So, before we move on to further sections in this chapter, I wanted to review what we've covered so far in terms of polar and other symmetries. Find ways to use paths that are common, radial and rotational paths, to simplify our calculations. To do so, we need to first review polar unit vectors. The radial unit vector is just a vector of x, y divided by its magnitude, so the point vectorized, made a unit vector. And the angular unit vector is the swapping of the two components, negating one of them, this one, to make it go counterclockwise, to give us our direction moving around the circle. So here to draw a point. At any particular point on a curve, the radial direction is pointing outward, and the angular direction is pointing along the curve, along the circular curve. And notice that they maintain a right angle between them, which means that they dot to zero. That's a very handy thing that we'll see later, is that these two unit vectors always dot to zero, just like I hat and j hat, directions of x and y, dot to zero. There's no overlap in a sense. So we have two main paths that we're going to look at for symmetry. Either a rotational path, a path that's going around a circle, or a radial path, a path that is moving inward or outward along a constant angle. So a rotational path has a constant radius, rotational path. And here, a radial path has a constant angle. So those are one way to describe these paths very briefly. Now, with a rotational path, our movement is always along the angular direction and never anywhere along the radial direction. Whereas a radial path is always moving along the radial unit vector and never changing along the angular unit vector. And again, those two are always 9 degrees to one another, and they dot to zero. Okay, so let's use an example to simplify our work calculations. Again, work is the force or the field dotted with dr, the direction of the path, the change as we move around. So before we do an example, let's just look at how these drs are developed in terms of polar coordinates. Well, since our rotational path has no change in the radial direction, the dr change will only be in the angular direction, and that the amount of that change is based upon the length of this arc on the circle. And the length of the arc is the radius times the small change in theta. So we end up with an r d theta times the angular direction. Then, for a radial path, since we're only moving in the radial direction, the change on that path is simply the change in the radius, dr, moving in the radial direction. There's no angular change, there's no d theta, no use of theta, it's only moving the radial direction. So that's what our path direction will be. It's either r d theta, theta direction, or dr in the r direction. So our example 1, we'll look at a 2D inverse square law. Now, a 3D inverse square law is an example used for the force of gravity. 2D square law is kind of a version of it, simpler version. So in this example, our field is described as a minus k times x, y, all divided by square root of x squared plus y squared cubed. Now you may think, cubed, I thought it was squared. Well, when we write it in polar coordinates, we can see the inverse square law. So if we factor out the radial direction, which is pretty obvious right there, x and y, we see what is left over. What's the magnitude left over? It's a minus k divided by multiples of the radius. Okay, well, how many? Well, we took one of them to give us a unit vector. And so we have two left, r squared. So here is our inverse square law. That's all it is, just saying that the magnitude is inversely proportional to the radius squared, or the distance squared. Okay. We want to find, I'll use a different color here. Find the work done by this field to move an object along the line 1, 1 to A as A increases. We'll just say it goes to infinity. So first off, this is a radial field that's pulling inwards, and as we're moving an object from 1, 1 outwards, this work is negative. So it's obvious the work is negative here. Now what this question is really asking us is, how much work do we have to put in to overcome the force of this phenomena? So gravity, for example. What is the amount of work we're needed to overcome the force of gravity to move an object from 1, 1 to A? So in our case, the answer here will be negative, but the flip side of that, the positive or absolute value of that, will be the amount of work we need to put into it, because the field itself is working against us. Okay. So we set up, we first think about our path from 1, 1 to AA. That is a constant angle. If you want to think of tangent theta equals 1, that's an easy way to think of it. It's a constant angle of pi over 4, but let's not worry too much about that. So we have our constant angle path, which means that we're going to dot our field with dr in the radial direction. Now the field we have to work with is minus k over r squared in the radial direction, and we're dotting it with dr in the radial direction. And let's set up our limits. Well, our curve will be along a radius starting at square root of 2 and ending at a radius of square root of a squared plus a squared. That's a root 2. So starting radius, root 2, ending radius, a root 2. Okay, now let's dot these components together. Well, we have the scalars. negative k, and I'll write this as r to the negative 2 dr. And then we have ur dotted with ur. Now these are both unit vectors. And when we dot a unit vector with itself, it's like I hat dotted with I hat, we always get 1. So unit vectors dotted with themselves give us 1, and it really just reduces our line integral over multiple components to just a single integral in the radial direction. So we integrate out. Negative k. We integrate, that gives us an r to the negative 1 divided by negative 1 from square root of 2 to a root 2. Plug in our values. Well, first, those signs will cancel. We have a common k, and we first plug in a root 2, and then we subtract, plug in root 2. Now, there's some algebra we could do to make this look a little prettier, but I'm interested in the limit as a goes to infinity, and right now, I can let a go to infinity. So limit as a goes to infinity of the work equals k times 0 minus 1 over root 2 is a minus k over root 2. Okay, so we found the work. It is negative, just like we predicted, based upon the radial field pulling in. And what's really surprising, actually, is that there is a finite amount of work. We've run into this problem before in Calc 2, and again, we keep running into this again and again. This is an example where we have a path of infinite length. We're going from root 2 radius to infinity as a radius. But our work done, the integral over that infinite length, is finite. Now, what does that mean? Well, let's imagine that this was the work done for our gravitational field. It's not quite the right constant. We get a root 3 instead of root 2 based upon 3-dimensional space instead of 2-dimensional space. But it's very similar. In 3D, you get a very similar negative work done, or work that you have to overcome to move an object from the Earth's surface or near the Earth's surface outward to the edge of the galaxy, assuming that the Earth is the only thing there. So what this is calculating is how much work it takes to escape the effect of Earth's gravitational field. And the work to escape the Earth's gravitational field is finite. And if you think about that a little bit longer, that was that idea that we have a finite amount of work or energy required to escape a gravitational field is what makes space flight possible. Now, you may think building spaceships is what makes space flight possible. Yes, okay. This is what proved to scientists, to physicists, that we could build spaceships to get away from Earth's gravitational field. We have to go quite a ways out. Earth's gravitational field continues to pull on astronauts and rockets a fair amount into space. I mean, it's diminishing, of course, but it has quite an effect. So, a finite amount of energy required, or work done, calculated over an infinite path from near the surface all the way out. Okay, so there's an example. Again, what did we do? We looked to see if the angle was constant or if the radius was constant. In this case, the angle was constant, and so we were able to turn our change in path, our dr, or path direction, into just change in r in the radial direction. Okay, so now let's look at another example.